Welcome back. So, in the last lecture we were talking about that how global positioning system or the GPS can help us in monitoring the ongoing deformation. This is what I was talking about, the elastic rebound theory. So, for example, if you are having an active fault which is passing through any region, okay, and the deformation is on that particular fault, and what will happen that over the time before it triggers an earthquake, okay, before it slip, it will accumulate some deformation, okay, that is elastic deformation, and you may notice that there is some deformation on the land, okay. So, if you look at this boundary, it got deformed, and finally when it rupture or what we could say fracture, okay, it will displace it, okay. So, this deformation can be monitored using either satellite images if you are taking continuously, okay, and monitoring that area very closely, or by putting the GPS stations across this, okay. So, that will help. Okay. So, for example, you are having the GPS station over here, then that will move, okay. So, this helps in identifying the accumulation of strain along the fault line, and finally we will have the rupture, that is what we call it will accompany an earthquake. This is one of the example from San Andreas fault again, where they put number of GPS stations, okay, which are numbered in 1, 2, 3, and then it goes up to 15. Okay. So, what they have found was that over the time they got displaced. Okay. So, for example, there is a fault line here, this is the measurements which they have put on the graph. So, you are having maximum offset which they were able to pick up was 905 millimeter, and endpoints was showing the displacement of, that is the endpoints here. Okay. The endpoints were showing the displacement of around 885 millimeter, and best fit line shows the displacement. So, overall average displacement which they found was around 780 meters or so. So, these are the GPS points which shows the displacement, and then end point is here. Okay. So, you are having the maximum displacement between these 2 points here. Okay. So, if you closely monitor any fault, you will be able to pick up the displacement or the deformation which is going on along that fault. Okay. This partly we have discussed about the recurrence interval and all that, and then another part which has been shown here is the portion which we were talking about, the elastic rebound theory. Now, there are a couple of GPS stations in Nepal and in China, but in India also now we have initiated with the help of Ministry of Earth Science, we are putting many GPS stations, and we have now recently we have a new center, National Seismological Center under the MOES, which is going to monitor this GPS movements. Okay. So, GPS measurements have been also now, not many stations have been put in the Indian side over here, and now recently we are going to put more 15 to 20 stations in this region, okay, which will help us in understanding that how the faults are moving. So, the blue arrows which you see here are the indicators of then how the plate is moving with respect to one another. Okay. So, here if you see this all vectors are going towards northeast, okay, northeast, whereas there are few vectors which are showing that they are moving in this direction, that is southeast. Okay. So, this suggests that this region of Tibet has been pinching out from this area, okay, because of the ongoing collision. So, we have if you look at here, this size of the arrow is 20 millimeter per year. So, we are having the convergence which is more than 20 millimeter in this particular region in the Himalaya, across the Himalayas. Further, in the part of the earthquake prediction and forecasting and prediction, earthquake prediction has had few successes. Okay. Earthquake precursors one can monitor. People have been working on this part also, that is the suspicious behavior of animals. Okay. And this is very time bound. Maybe you can pick up this behavior, unusual behavior of the animals just before the earthquake. Okay. And then people have been talking about the unusual signals of electrical signals, because of course we are engulfed with the electromagnetic energy and there will be definitely change in that. Okay. Many large earthquakes are preceded by small earthquakes, what we call foreshocks. So, if we monitor the foreshocks, you may have a chance to identify the big event which is following the foreshocks. Okay. Now, in 1975, Haichen earthquake was predicted. Okay. Chinese authorities used series of foreshocks as an warning to anticipate the Haichen earthquake in 1975. This was been predicted and they saved many people. Okay. So, finally, what we are interested in, having understanding of the faults, having understanding of the earthquake behavior and all that, we want to know that what is the probability, okay, of the earthquake in along the plate boundaries or away from the plate boundaries. So, this is one of the example which has been given here, that the red areas are having the probability of high probability of earthquakes, okay, 60 to 100%. Okay. So, likewise we can have for India also, that which portion of the Indian plate along the Himalaya is having the higher probability of earthquake in near future, and that can improve the hazard assessment part, seismic hazard assessment part. This we have already talked, so I will just move ahead, that what are the fault scarps and all that. So, if you are having a displacement along a fault, okay, where this is a normal fault, where this block has, this is the hanging wall and this one is your foot wall. Okay. So, this wall has moved down, hanging wall moved down with compared to that, okay, will result into this. So, the surface manifestation is your fault scarp, and then what the base of it we call the fault trace, and this is a fault plane here. Okay. And then we have the epicenter and the focus. This is the place where the earthquake energy will be released, and exactly on the top of the surface, this is what we call the epicenter. Okay. Now, this part we have talked about, why it is important, the active faults. Now, what is an active fault topography, okay, and how we identify? I will show a couple of pictures of the fault topography, and then we will move ahead in this course. Okay. Earthquakes is caused by rapid movement of the fault in subsurface. Okay. So, there is in subsurface displacement which is coming right up to the surface or the ground, and that what we call the fault topography, or the fault scarp is again what we call the active fault topography. So, the rupture or the displacement in the subsurface often reaches the surface, okay, when the magnitude is generally over, moment magnitude is above 7 to 7.5. If you are having less magnitude 5.5 or so, no rupture will be there, and then those earthquakes are not going to harm much, okay, because it will not result into the large amount of shaking of the area. Hence, we are not very much worried of the 5 magnitude earthquake and all that. But even 6.5 magnitude earthquake in India will be hazardous, because Our buildings are not capable to withstand that much of shaking, which could be produced by 6.5 or 6.9 magnitude earthquake. So, mostly the surface ruptures which we see or the displacements along the faults which are coming right up to the surface, those surface ruptures are produced by earthquakes with magnitude greater than 7 or 7.5. So, the fault that reaches the surface is called the active fault in the narrow sense. Okay. However, if you remember one cartoon which we were talking about, that there are times where we will not have the rupture coming right up to the surface. That what we call the earthquake has been triggered on a blind fault. Okay. And this happens in most of the time. Okay. The earthquake cannot produce the surface rupture, but it took place. Okay. And it result into the damage, it result into the ground shaking and all that. Okay. So, no signatures on the surface. Okay. So, sometimes we try to correlate or find out such signatures or the evidence, okay, from the literature, try to understand. For example, in recent past, say 2001 Bhuj earthquake was on blind fault. No surface rupture came right to the surface. 2015 Gorkha earthquake was did not rupture the surface. So, historical documentation is also is important to be noted, and reporting of such earthquake is also extremely important. So, what we did was that immediately after 2001 Bhuj earthquake, we went into the field, we got some deformational features which were secondary, but we noted down, we reported that. Okay. And even in 2015 Gorkha earthquake and followed by the Kodari earthquake, we mapped the surface expressions where we can again say that it was in secondary, but we were able to pick up some signatures of the related to that deformation. So, this is what it explains in the simplistic model of the fault blindness. Okay. So, if you are having a small earthquake, okay, or if you are having a smaller area getting ruptured, it will not see the surface. Okay. It remains blind. Some intermediate magnitude earthquakes will come right up to the surface, okay, or the rupture comes up right up to the ground, but very small area will get ruptured, and very often these signatures will be obscured or maybe deleted or eroded, we can say, from the surface. But if you are having a large magnitude earthquake, okay, then we will have a prominent surface manifestation. So, this what we are now, not all earthquakes are blind, okay, or will occur on blind fault, but there are few. So, we have to take into consideration those signature also. So, what we do is that we try to concentrate, if we are having, we know that in most of the in some areas, if you are having most of the earthquakes are occurring on a blind fault, then we try to take into consideration the secondary features. Okay. Now, these secondary features are, for example, liquefaction. So, if you are having the liquefaction preserved, because liquefaction will occur at any place, okay, it does not have any boundary. Okay. It may be because of the earthquake which has been triggered 200 kilometers away, but if it is powerful, if it is nevertheless no problems if they are blind, but then also it will result into the liquefaction. Okay. So, those things we can, and even the landslip. Okay. So, landslides, landslip, liquefaction, such features can be taken into consideration to identify the earthquakes which occurred on a blind fault. Okay. And if they are large enough to rupture the surface, then we have the active fault topography to be identified. So, what is an active fault mapping? Okay, what we do in the active fault mapping part. Okay, and this is like I told that we are in process of building up a digital active fault map of Himalaya and Kutch. Okay, so active fault mapping is to look for the fault topography created by paleo earthquakes, ancient earthquakes. Okay, for example, fault scarps, warped or folded surfaces, pressure edges, back tilted surfaces, offset or deflected streams. Okay. I was showing one example of the deflected streams, okay, along the San Andreas fault. So, this is what is the fault topography, part of the fault topography, and the fault scarp. Maybe in the next slide I will show that what are the fault scarps and the warped surfaces. Okay, because when there is a deformation, so for example, if you are having the different layers here, and if you are folding it, okay, and there is a fault here, so you are folding it. So, what will happen? So, this will be displaced along the fault and they will get folded. So, this manifestation on the surface is termed as fault scarp. And in some cases, what we have seen mostly is that the surfaces, this is the surface, it will be like this. Okay. So, there is a fault here, fault plane which has moved like this. So, this is what we call back tilting. So, the surface has been tilted towards the back, and this is very common in most of the fold and thrust builds. Okay. And what we have is one of the mightiest one is the Himalaya. Okay. So, we will come across such manifestations, okay, on the surface. That is what is the fault topography, and we are going to pick up those. Okay. So, for example, on the surface, if you are having a strike slip, then the streams which are flowing will be deflected, okay, along this one. So, this is your sense of movement, the stream flowing are getting offset. So, this is another feature which one can pick up as a part of the active fault mapping. Then satellite photos. So, what we do is we use very high resolution satellite photographs, because we do not want to miss even a topography which has been created by paleo earthquake, having the surface manifestation of maybe hardly 1 meter or 1.5 meter or less than that also. Okay. So, we are very precise in mapping those. So, hence we have to use very high resolution satellite photographs. Okay. So, that is what we call the satellite photo interpretation, is the most basic technique for identifying the active fault. We cannot detect any active fault without satellite data, okay, especially on the active fault unreported by historical accounts. So, if there is no historical account, how you are going to identify those ruptures, okay, or the surface manifestations of the paleo earthquakes? Okay. You need to use the satellite data. So, if you are having expert eyes to identify such features which we have been talking about, either the fault scarp, warped surfaces, pressure edges, back tilted surfaces, deflected streams, you will be able to pick up those on the surface, okay. And it is difficult to go in field and map those, okay, for the first, as a first step. Okay. So, we use high resolution satellite photographs, we prepare the basic maps and go in field and map it. Okay. So, this is a flow chart how we do the studies, okay, like paleoseismic studies, or how we are doing and what is the outcome of that. So, first what we do is the photo interpretation, satellite photo interpretation, also the literature survey. So, from the literature survey we try to look at the historical documents, okay. And during the historical documents, it is quite possible that you may come across a very mythological language, okay, or maybe in philosophical language talking about the earthquakes, okay. In many ancient chronicles we will be able to find this. Okay, and there is a famous professor, Professor Iyengar from IISc Bangalore, who documented this and translated, okay, from the Babarnama, Akbarnama and Sanskrit literature, and also from some Vedic literature. He tried to translate and tried to understand that what exactly they want to talk about if they have recorded any earthquake. Okay, and there is a very beautiful paper which talks about the ancient earthquakes from India. Okay. That helps us in knowing that, okay, fine, this region had a big earthquake in the past. Okay. Probably the way of describing it may be linked with some religion or maybe some myths, but ultimately we need to understand that what exactly they are talking about. Okay. Then we do the field survey to identify those features which we have picked up from the satellite data. Then we try to select the site for trenching. Okay. So, this is what we do. We try to, because whenever there is an earthquake or whenever the past earthquakes, the deformation is preserved within the sediments and on the surface. Okay. So, that what we call the earthquake signatures are preserved in sediment stratigraphy and in form of landforms. Okay. So, this is displaced landforms. Okay. Displaced, or we can say deformed landforms. Okay. So, we try to do that, and then trench investigation, we try to look at that how many times this fault was ruptured in the past, and we date those sediments or the buried coal, or maybe you can say charcoal, okay, with the help of different techniques. Okay. And then we try to understand that when exactly that earthquake took place, okay, in the past. Then based on the chronology of the layers or the sediments, we identify the earthquakes. Okay. So, we try to bracket the events when exactly that earthquake took place. Okay. Then we try to compare with the historical data. If it has been recorded, we try to compare it, and then likelihood of that we can suggest that this earthquake is the earthquake which occurred during this period. Okay. As I told in my previous slide, I was talking about that there is a record of AD 1803 earthquake and AD 1505 earthquake in Babarnama and Akbarnama and Tariq-e-Hasan. Okay. These are there. Okay. And one novel is there named as Devanagari, which also talks about this earthquake. Okay. And even during this period, Britishers were around, so they have recorded this earthquake and documented. So, that data particularly we take into consideration and then try to correlate if it is available. Okay. And this earthquake was at the time when the Mughals were here, so they have recorded the 1505, and the another one was by Britishers also. Okay. And then finally, this data is important for the seismic hazard assessment based on the time prediction model. Okay. So, if I say that, okay, fine, the earthquake, if there is this is your site here, and then fault is somewhere here, okay, and then earthquake has occurred across or along this fault, okay, then you can easily talk about that what is the distance here between the source and your site, and what will be expected seismic shaking. Okay. So, you can talk about the peak ground acceleration and all that. Even based on the paleoseismic studies, you will be able to dig out the magnitude, you will be able to talk about the slip during single event, you will be able to talk about the sense of fault, whether it is a thrust fault or a reverse fault or a strike slip fault. So, this data is extremely important for us to have a proper seismic hazard assessment in any seismically active regions. Okay. And of course, the location of fault is more important because we should not put any structure on those faults. Okay. This is what I was talking about, that this is from Bhuj area, and the section and the topography is both can be seen in this photograph. Okay. So, we have the surface manifestation here. Now, this has been created because of the displacement along this fault. Okay. And you can mark the displacement very clearly here. You have this contact and you have this contact over here. So, this is your net displacement, and the surface which is getting warped, okay, can be seen because of this displacement here. I will remove the lines here. So, now if you can see here, we have this is the contact here, and because of the displacement along this fault, we have the surface manifestation. So, this before the displacement could have been something straight, okay, like this, okay, but because of the displacement now it has moved like this. There is a displacement over here. Okay. So, this is what we call the fault topography, and if you look at in this section, then you can measure and take out a lot of information out of this, that how much was the displacement during the most recent event and what was the angle of the fault and all that. Okay. Now, based on this, as we have been talking about, this is a reverse fault, okay, because the angle is greater than 45 degrees. There is another surface manifestation photograph showing of 1995 Kobe earthquake, and if you carefully see here, this is the surface manifestation of the Kobe earthquake. It just passed close to this house. Okay. So, this house was been saved, but if you can see here, there is a this is the compound wall or the boundary which got displaced, and the displacement was this wall, this side wall moved up, and then there was a lateral movement. Okay. So, it is in what we call the right lateral movement took place. Okay. So, the block moved like this. This side went up and laterally it moved. Okay. So, it is an oblique slip fault, we can say. So, close up of that house and the wall, which you can see here. Okay. So, fault just crossed this one here. So, this side is up, this is down, and with some lateral displacement. So, what they did was, after 1995 Kobe earthquake, they occupied this area. The geologists and the city people, they occupied this area and they converted this into a museum. Okay. So, the photograph, the next photograph which I am showing is been taken from here, viewing this side. Okay. So, this part is a museum here, and this is also now, this house is also a part of the museum. They have taken away this house. Okay. So, this was a very deadly event which took place in Japan in 1995. Now, Japan has lot many plates which are subducting below each other. Okay. And the mainland of Japan, there is islands of Japan are sitting on the some part in the North American plate and some on the Eurasian plate, and where we are having the Philippine plate subducting below it, and here the Pacific plate subducting along the Nankai trough, what they call, and then Japan trench. Okay. So, this we are having. So, this was an earthquake which was been which ruptured the area here. Okay. So, this is in Honshu mainland. Kobe was the most devastating city, and then we are having an Awaji island. Okay. So, this fault is the part of the MTL, main median tectonic line, very much similar to what we were talking about the San Andreas fault system. So, earthquake occurred here and the rupture moved on. So, we will continue in the next lecture. Thank you so much.